Hello, hello, zdravo.
Zdravo.
Како сме?
Добро.
Може вака дур чекаме да дојдат сите да се позбориме на македонски, па после тоа ќе преминеме на англиски.
Може, слободно.
Како сте денес, како денот? Расположени за настан?
Стојанче се слушаме од 6 саца бајле, така да сега веќе е касно за нас, да.
Добро. Glad to hear. Обично пред секој настан чекаме некоја минута-две да не се уклучат attendees на настанот, па да им даеме нели шанса да не фатат од сам старт.
Не може да ни почне денот ако не си направиме муабетот со бајле.
Така.
Ма каков е тој ден ако не почне без AI?
Така е.
Точно. Башка AI, first letter of the alphabet. It makes sense. Здраво, Томислав.
Ало, се слушаме?
Да.
Сега само да наместам тука со слушалки со камера, да се средам убаво да видам.
Okay, so it's 6 p.m. So now I'm going to start speaking in English language since we have a lot of participants coming from other countries as well. I would like to welcome you all. First of all, I would like to welcome the special guest stars and the team who is behind this project. And we have the initiator, PhD Professor Marian Gushev, as well as the data science team who has been contributing to this project for the past, I believe, few months or maybe in the past year. I would like to start off by saying that we will give the attendees another minute or two to join us all. And plus, we are still waiting for Alexander, who is also another team member, part of the data science team working on this project. Welcome, Stojancho. Welcome, PhD Professor Marian Gushev, and welcome, Tomislav. And here we also have Alexander Stankovsky joining us at this discussion. Now that we have everyone on the call, I would like to say warm welcome. And once again, welcome to everyone who is joining us tonight for the Tech Tuesdays event, which is powered and organized by Intertech. The main speaker and presenter at this event is a dear colleague of mine, Stojancho, who is also known as Striki in the AI community here in Macedonia, and I believe outside from Macedonia as well. He has been in the IT field for over 20 years, but in the last 12 years, he pushed himself to grow his knowledge in data mining, predictive analysis, machine learning, AI, deep learning, and for the past 2 years, he's focused on NLP with transformers and ML and AI for fintech. Stojancho, welcome. Also on this call, we have the PhD professor, Marian Gushev, who is also CEO and founder of Innovation, a company who has been working on this project that we're going to discuss during this event. It is a great honor to have him on the call. First of all, I mean, there's so many wonderful things to say about him. I would like to mention at least two. One of them is that back in 2012, he was awarded with the award Scientist of the Year, and recently on the World Day of Science Day for Peace and Development, he received the award and the recognition for contributor with the highest number of scientific publications in the past decade in the field of Web of Science. So Professor Marian Gushev, it's a great honor to have you on this call, and thank you for joining us today. And last but not least, we have Tomislav and Alexander, who are students at the Faculty of Electrical Engineering, Computer Science and Informatics here in Skopje. They're both part of the data science team, as I said at the very beginning, and they will be also participating in this presentation as we go along. I would like to officially announce this event to start and begin. And I would like firstly to invite Professor Marian Gushev to say a few words before we start with the presentation by Stojancho Tujarski. Professor, welcome.
Okay, nice to meet you, and thank you for very nice words that were said to me. And yes, I always accompanied by students, and I always like to motivate them, and I hope that my awards will be their awards very soon. Thank you.
Okay, I believe that before we start, I would just like to say to all attendees that the agenda is we first give a presentation and discuss more about this project and actually how data science and machine learning can help in preventing or predicting heart diseases. And then after the presentations, we will have a Q&A session where you can ask all participants questions related to this project or anything that you feel like asking them. Stojancho, you can take the floor. I believe you already have a sharing screen permission. Just let me know if it's okay on your side.
I will try. Not again. Okay, I'll have to restart Zoom because it is asking for permission for sharing screen. And I will rejoin immediately.
Okay, no problem.
Well, this is normally for Macintosh.
Yeah.
Private
this usually happens in online events, so yeah.
Yeah, these are one of the challenges that we have to solve. GDPR, it's protection of data, and we are talking about medical data, and medical data is also a huge problem. So data should stay within the country, not get out of the country. So for example, if you have a solution and sell it in Italy, then you have to build a server there.
Okay.
Yeah, okay.
Stojancho? Yep, I can see the presentation.
Can you see my screen? Okay,
yep.
That's great.
Take it away.
Okay. Yep. Slideshow. Just to set up my PowerPoint. Okay, so this is presentation about take a seat and if you're expecting a heart attack and why. I'll try to elaborate in the following several minutes. I'll start with some facts. Science is progressing with a speed that is rapidly increasing, and visualized, you can see the number of articles that appeared on ArXiv publication, ArXiv site over time, and it is increasing almost exponentially. So this is one fact. Fact number 0. This leads how to fact number 1, that you simply have no time to read everything that appears on the horizon. Simply too much, too many new things, and very quick expansion in the all areas in the science all over the world. And as consequence of the second fact, you simply cannot be constantly in line with all the latest happenings in some previously designated boundary of your interest. For example, if 30 years ago, if I was interested in IT, then in software, last 12 years in AI only, it is harder and harder for me to be in line with all the achievements in that area. And I presume that that is case in every field of the science. So my point is that you have to be you have to specialize deeply in your area, and you narrow down your focus of your interest if you want to be to stay in line with the latest happenings. Otherwise, it is you see there are only 24 hours per day, so you cannot read everything that appears on the daily basis. This means that you have to decide where you would like to be in line with the latest trends, and sometimes maybe the area that is bounded by your of your interest is not visibly fruitful. It is simply fruitless from time to time. Let's say, for example, the theoretic mathematics, where mathematicians are examining theories and theories years before they are applied somewhere in the reality. Nevertheless, let's say data science, for example. What is data science? Data science is nothing more but playing with numbers. So you have collected a lot of numbers, and you use them to train some models that generates nothing more but more numbers. When you call predictions then. And it's really, when you summarize it in this way, which is true, then it is really not a big deal. Because if you generate numbers out of the context, then you're not doing anything useful in particular. Your data science knowledge is valuable if and only if it creates models which predictions mean something in the real world. Otherwise, they are useless, and they are subject of your joy, maybe, if you're enjoying playing with numbers, like me, for example. So in order to make some real use of data science, you have no other choice but to make it useful in some other areas that are beyond your scope of and boundaries of interest and knowledge. Because once again, your scope of your interest and your knowledge is only data science or number crunching, the skills and so on. Without applying them somewhere in the real world, your knowledge is gone with the wind. It's fruitless. So what you need in reality is you have to build some bridge to some real business case and some business domain where you will be able to apply your knowledge, for example, in data science. And the rest of the presentation is simply telling a story about one of that possible bridges that I'm passing over with help of the professor and the other guys in the team. So in particular, the bridges between cardiology and data science. And But let's start from the beginning. Maybe not the biggest problem, but for sure one of the biggest problems to apply data science everywhere, anywhere in the medicine is lack of training data sets, and that's because the clinics are simply forbidden to, by the law, to provide data collected for their patients and to share them with another clinics, for example. And I cannot even imagine I cannot even imagine them sharing that data with guys interested to apply some machine learning and artificial intelligence algorithms, methods, train models based on that data. And from my perspective, that is very precious data because it can be used very wisely, but because of some law enforcements and laws in the field, and there is a very strong reasoning behind that laws. Authorities are not allowed to share that data, but there are some exceptions. And when I started to work with Professor Gushev, he pointed to me to Sionet.org site, and that is really a magic keyword, magic phrase for me, because I started learning about this thing. And it was kind of, okay, I already have seen this image, but what exactly does it mean? I had no idea. And I started to learn and watched several means up to 7 or 8 courses on Udemy about ECG readings and so on and so on. But I started to get inside the problematic and to figure out what are these images talking about. And the main advantage of the Sionet site is that contains a lot of ECG readings databases. I tried to count them, and there were more than 100, I would say. And if you sum up all of the size of the databases, you will reach 15 gigabytes for sure, compressed. And which is even more important, some of them are annotated. Annotated means that each heartbeat in the database, in each ECG recording within the database, is manually classified by the trained professionals, cardiologists. And there is standardized way for annotating this data. For example, the data has to be annotated in parallel by 2 cardiologists, and if their findings are same, then that is golden true. Otherwise, if they have different findings, then the third cardiologist is taking the stage and decides which one of the previous 2 cardiologists has correct annotation. And this standard procedure for generating this kind of annotations. And from my point of view, this is priceless. Like kid in a candy shop, you know. So I said more than 100, but actually there are more than 200 databases. And also one very important thing, all of the databases are digitalized in a standardized way, meaning that the format of the recordings of the files is preserved all of the datasets. This means that actually you can read and process all of the readings with the same software. and this is a very powerful fact because 15 gigabytes of raw data in front of under your fingers is something that makes me trembling, you know. But anyway, for example, the most famous database is MIT database. It contains 24 hours of 2-channel ambulatory ECG recordings. The recordings are 2-channel. You see, when you go into a hospital and they're performing, and doctors are performing ECG on you, or with those electrodes all over your chest and your limbs, they are collecting 12 channels in more restricted areas. There are 2-channel ECG recordings, and you have so you have the database of more than 100,000 annotated heartbeats with appropriate cardiology diagnosis, meaning that cardiologists not only that they are classifying each heartbeat in systematical way by standardized classification. Up to I think at about 15 or 17 classes of the heartbeats, but they are providing insights about noted diagnoses over the ECG recordings. For example, atrial fibrillations. And what can we do with these data sets? In short, a lot. For example, maybe it's too optimistic to say, but it might be true. Predicting incoming heart alert. It is not really rocket science unless you have some cardiologist that can explain the atrial fibrillations to you. And what Wikipedia is saying about atrial fibrillations is this: a lot of words. In short, the heart is in trouble, and this actually means potential of incoming heart attack. Not that heart attack will appear for sure. That is not possible to predict such kind of things as anything else in the medicine and everywhere in the real world, actually. But this means increased probability. And when you have patients with high risk, treating them well in such occasions may mean a lot of them. Maybe this can be situations of life or death for them. So this is atrial fibrillation. In short, if you notice atrial fibrillation, then you have higher chances to have a heart attack in the next 15 minutes. So take a seat and call 911. What would we need to make a real use of this of all of these possibilities? We have to have attached ECG device that is wearable, that you can put on your chest and make him stay there for a while. Then you need an AI model, trained model that can recognize atrial fibrillations, and you need alerting mechanism that will alert you and your doctor. Or let's say automatically call 911 with giving your location, which is doable, pretty much doable with today's mobile phones and so on. So this is example of one wearable SDG device. Sorry guys, no image with the lady here. I tried, but it is hardware. It is easy. It is relatively easy to make such kind of hardware. There are already several of those devices on the market. What is missing here? And yeah, not forget to stay away from watches. I think that iWatch is also capable of recording ECGs, but it is only one channel, and it is far from being precise enough to be used in for clinical cases and to be reliable enough for patients that really needs cardiac treatment. On this slide, I'm mentioning the course that on Udemy that made the strongest impression on me. There is one Indian doctor that is explaining ECG 7 hours of the course in front of his students, and watching him, you simply cannot not understand what is going on. It's impossible not to understand what is he talking about. Guy is natural, really. We have hardware that is able to wearable hardware that is able to read and record ECG. Next part is AI, and not that tough thing. We did it last year. We published one paper with this description how the state-of-the-art results on recognizing atrial fibrillations over MITDB dataset, accuracy 99%, and we submitted that paper on the TAIL4 conference last year. It was accepted. Now we are waiting for him to be indexed and published and announced in the scientific circles. Anyway, the technology is here. We can recognize atrial fibrillations when they appear, and this provides possibility to act upon that. How do we do that? We didn't do, literally speaking, nothing special. All we do was proper feature extraction, one hot encoding of categorical features, data normalization, and simply applying XGBoost and provide a binary classifier over this. And that's it. Really nothing special. Everything was, literally speaking, by the book, by the every possible data science course for machine learning you can find everywhere. And we did it, and we reached that accuracy. So it is not that easy. It just matters. What matters here is to find a real business value of your knowledge, of crunching numbers, and apply them to. And we found one of these cases, and we applied data science there. And how this can be used? Plain and simple for alerting mechanisms. For example, SMS messages can be used to be sent to designated cardiologist. Annoying sound from your phone. Let's say while you're driving, your heart starting to beat like crazy, and the problems and generating atrial fibrillations. In some cases, maybe just trigger to send some ambulance to be there in place if needed, just in case. When we put all of these things in this way, it is pretty much obvious. But while I was writing this article, I started to in this presentation, I started to look on internet for such kind of devices, and I found this this article published 2019, where they are talking about the first AI-driven wearable heart monitor, and it was mind-blowing for me. I mean, why this took so long when it is so obvious that this can be done, and is the market saturated? About the market saturation, I would say no, because if the first device is appeared to let's say 2.5 years ago, then market is far away from saturation. So we cannot even talk about that. And about why this took so long, I really have no idea, because it is so obvious for me. Can we do something else with MITDB database? For example, the next thing I'm working with the professor and with his team over MIT database is Hardbit clustering. So the key idea is we isolate single Hardbit voltages, normalize them, meaning we stretch them to 100 points, exactly 100 points, meaning normalization. Okay, then make them flat, because if you have ECG, then you have some wave-like recording, but you have to normalize it to be flat with the main course, and in order to have a comparable heartbeats, and then run any common sense clustering mechanism, clustering algorithm. What can be result for this? How this can be used? For example, for anomaly detection, if you make proper clusters from ECG recordings, then the points that are far away from the centroids of the clusters are by definition outliers. And outliers can be, for example, noise in the ECG recordings. And this is result. I hope that you can recognize which one is noise and which one is proper ECG recording. According this image, we generated this image several days ago with help of Alexander. So there are wide variety of things that you can do, and you can build something reasonable and helpful with in the presence of this MITDB database. How you can use this? How to make some valid business case for this? How about if you can detect outliers, then you can build the triggers that do something, some alerting, for example, when the outliers appear. And now it is tricky to figure out what exactly the outlier is, but for sure possible outliers are when ECG recorder started malfunctioning. This is one possible use case for this, and then for example, if there are some sequences of ECG recordings that are too noisy, even for the cardiologists to be taken care of, then simply strip them away, because cardiologists are becoming very nervous in presence of that kind of readings. And now I'll start talking about some other ideas how to apply AI with MITDB. And 2020 was year of a triumph for transformers initiated in NLP. Transformers are, okay, not Transformers by Michael Bay with Megan Fox, among others. Here we're talking about transformers as a neural network architecture that provided a really huge breakthrough in NLP area. And it is out of scope of this presentation to try to explain multi-head attentions and input embeddings and positional encodings and so on and so forth. But in short, they are a very powerful mechanism. Now, how this relates to cardiology? I haven't seen something in written form about something similar. This is my brainstorming. But let's formalize this on the following way. Data science is all about crunching numbers and producing new numbers, and we figured that out. This is its weakness, but also its strength at the same time. Because if you when you are not bound to some specific domain, like crunching numbers, then you can apply your methods all over the world where you can reach numbers. And now, starting with 2020, we have technology that is proven to be superior to other similar technologies in NLP area. And now my question was, why not to try to implement this exactly the same algorithm, the same neural network architecture in some another business domain, for example, cardiology. If we do that, we'll have BERT and GPT-2 trained over Hardbits. And BERT and GPT-2 are natural language models. And I will not go into details here. What is natural language model? Actually, maybe I should pinpoint some interesting things. For example, the point of BERT is BERT is an example of masked language modeling, where the model is capable of filling gaps in the texts with proper words, contextually correct, based on the provided tests during the training phase. So maybe nothing special, but very powerful, and I will explain this later. And GPT-2 is automatic blah 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 machine. He talks a lot. He is capable to extrapolate a given text with you give him let's say one sentence or let's say 10 words, and it's capable to generate 5 kilobytes of text or with preserved context based on these 10 words. So just give him a try and let him speak, and several times, and so on and so on and so on. So these are very basic explanations of what BERT and GPT-2 language models are doing. And now let's see how we can use this in cardiology. Foundation model is a new term coined by scientists at Stanford. I would say 4 or 5 months ago, and it is designated to describe a model that is not predictive but generative model, and it is trained in a self-supervised way, meaning that we are just feeding the model with a lot of data. And based of that based of that huge volume of data, the model is able to figure out the connections among a wide window of the words. For example, for bird, the window size is 512 words, and it is not that small amount of text. So heartbeats or words or heartbeats can be in this way can be treated in a contextual way, meaning that encoding for each heartbeat will take account its surrounding as well, not only data for specific atomic information, even it is word or heartbeat and so on and so forth. Now I'm talking still about BERT model. As I said, not that powerful thing when you're seeing that with masked language modeling. He's filling gaps in the text, so what? Nothing special. The main trick here is that when you have you spend, let's say, several weeks and huge amount of electricity, and you pay a lot of money for electricity, not for digging bitcoins, but for doing something really useful, and you're training a model that figures in self-supervised way. You're training the model that is capable to figure out the context of the things that you're feeding him. And self-supervised way means that the data is completely unlabeled. And why is this so useful? This is so useful because providing labeled data is a very expensive thing. You can afford yourself to label 15 gigabytes of ECGs. That's impossible. Just try to figure out how much money you'll have to pay for a cardiologist for that. Probably several billion of dollars. But now let's think about what can we bring on the stage with a model with BERT-like transformers-based architecture on the stage for ECG. As proven that as a working concept for NLP, having BERT in place for natural languages, you need up to 10 times less labeled data in order to properly train fine-tune, not retrain from scratch, but fine-tune existing model to any downstream task, meaning in supervised way, meaning classifications, for example, sentiment analysis classifications. So let's stick to the classifications right now. If you have BERT model trained with, like BERT2, trained with 70 gigabytes of texts, trained several weeks, then you need up to 10 times less labeled textual data to make to train a model for classification of any kind. And this concept is known as knowledge transfer. And I cannot imagine why this cannot be used for ECG recordings as well. So if you train ECG bird, I mean model with exactly the same architecture over ECG recordings in unsupervised way, using these 15 gigabytes of ECG recordings, then you'll have some good starting point to train any kind of classification or any other downstream task with 10 times less labeled data than you would need previously to achieve even better results. And that's the main advantage of this knowledge transfer. And having this in mind, actually, these days, nobody is training neural networks from scratch. Everybody is using already trained foundation models, and they are fine-tuning them. How about Hardgpt-2? So Hardgpt-2 is nothing but produce the most probable words in a given sentence of words. That's true. So blah 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 on scale, but the words are presented by the model by numbers and IDs of the words, and the model produces nothing more but numbers as well. And in reality, the model has absolutely no idea what he's talking about. Even that is contextually, even it is with completely preserved contexts. Preserving context is nothing. There is no magic actually in preserving context. This comes naturally by applying very sophisticated statistics over very huge amount of data. So it's plain statistic, nothing more, nothing magic here in this blah blah blah. But it's effective. Well, so if we train GPT-2 with ECG recordings, what we can get? We can provide a model where we can put into let's say 100 ECG recordings and tell the model, "Hi guy, please tell us what are the most probable next up to 5,000 heartbeats," and it will produce that with based on statistics and with preserved context. And well, I'm not sure how clear I'm explaining this concept, but and maybe all of this sounds like science fiction to you. And that was exactly the case when I was talking to most of the people a year ago about training neural network, fine-tuning neural networks to imitate Shakespeare and Blazhukowski. And then it was science fiction, but not anymore. And even more, Tomislav and me started working on this, and we made when you train models like BERT and GPT-2, the first step you have to do is to build a proper tokenizer. And we did a proper tokenizer, and we tokenized MITDB database. So it is possible. So the next step should be to encode using that tokenizer to encode the complete all of the databases available, and then train a model, and a lot of electricity, but again not for mining bitcoins, but for something useful. And it is not science fiction. And I hope that next year or two, I'll be able to prove that to you with some real results. these are the guys that are standing behind this this project. Guys, thank you very much for being my companionship. Just as notice for the visitor, for the watchers of this presentation, if anybody is willing to join, help, work on with us on training models or building software that will make real use of provided AI cases, feel free to reach anybody of us, and my personal email is streaky@streaky.ai, so reach me anytime, any place, anywhere, even on the street if you find me. Okay, so the final words, AI is still heavily uncharted territory, and it is in dramatically increased speed of development. And what is frustrating for me personally is that that even highly trained IT professionals cannot recognize properly the values of this technology. And when I'm talking to them about these AI things, they are acting like, hey, are you aware what are you talking about actually? But yeah, this reality, and the point is that even if high valuable IT professionals cannot figure out, cannot understand the values of these possibilities, how can we talk to other guys? All of this may look like science fiction to them, but this is very doable and very useful, and it is interesting and challenging topic to try to elaborate all of these things to some non-IT guys, but with business-wide perspective, where all of these things can be applied, and with coordination with them to make something useful. And this thing with alerting for incoming heart attack is only one very simple use case, and we can do much more than this. I'm sure in that. So the major the thing is to be in contact with the right persons that have correct domain knowledge that you can use in order to make something useful with the numbers that they are generating. And what are you good actually is to dealing with numbers. So deal with real numbers. Any questions?
Well, Stojancho, thank you for the wonderful presentation. We already have a question in the Q&A part here on Zoom. The question is, can we use GPT models for numeric tabular data classification or regression? If we can, does it contribute to better automatic feature engineering?
I'll answer the live on this. Sorry, what happened? Oops. Okay. We can train GPT models by providing tokenizers, tokens. And tokens are nothing but IDs of numbers. And in case of GPT-2, the GPT-2 was trained with a set of 52,000 tokens. So it was fed continuously with numbers between 1 and 52,000. So if you are able to produce that kind of tokens, not maybe 52,000, any kind of tokens, you can train a GPT-2 like model with that tokens. It literally speaking doesn't matter what that tokens means in the real world. The model will be, it's proven, the model will be trained will be trained correctly and will produce results with preserved semantic based on the previous on the previous tokens provided during the training. So you can apply it everywhere where you can produce token IDs.
Okay, thank you. We also have other questions that I received on email and also on chat. One of them is, if you can, somebody else also can join from Professor Gushev or Tomislav or Alexander if they feel okay to answer this question. It doesn't have to be you, Stojancho. Why did you choose XGBoost as a solution for the risk prediction?
Because I run AutoML solution, which shows that XGBoost is the best model for provided dataset. Now, it is fact that there is no golden rule that will pinpoint the correct model or correct algorithm for training data, for given training data, and all you have to have actually by definition is to apply all of the algorithms you know about. It is proven by no free lunch theorem mathematically. So you have no other choice but to try all of the algorithms and methods you know about. So stay armed with toolbox of a lot of models and try each of them. And there are libraries on internet in Python that are doing this for you in automatic way. So I run that procedures, and they showed that the XGBoost is the best performing model that produces models with the best accuracy over the training set, and therefore naturally I choose the XGBoost.
Okay, before we continue, I would we have another question in the Q&A session on Zoom, but I would like to invite and ask Tomislav and Alexander, since they're the young team members, because both of you and Professor Gushev are basically the goats of the project. How did they find any challenges while working on the project? In which way did you mentor them? Did they had any like strict deadlines in terms of everything that they had to do for this project? Tomislav or Alexander, you can both answer if you would like.
Yeah, well, want to jump in and correct Striki for the last question, why we use XGBoost. He said everything, but we didn't use AutoML. We used PyCaret, just to give where there's recommendations. It's a really good library out of the box.
That is more precise answer.
Yeah. In terms of difficulties, me personally that I had to overcome was for the first time working with bigger data than it could be loaded into the RAM memory. So in start, when we were still processing the data, we used the Dask, which is also a really good library for big data processing and data manipulation augmentation in order to encode and standardize the Hardbits. And yeah, that was the main point of the main difficulties as I see in the making of this project.
Okay.
Come on, guys, be honest.
I can point out.
You were wake up at 8 o'clock every day to talk with me, but that's it.
That was the beauty of it. Alexander, welcome.
Yeah, aside from the machine learning part, I can point out that the medical part of the project was a real challenge at the start. For example, understanding the beats, the heartbeats, how what's the difference, understanding how to interpret the annotations and every part of the medical data set from PhysioNet. We have to be precise when working with this project, so it was a real challenge to get started with the heartbeats and data sets. But once we got the ball rolling, now we're fine and everything's great.
We have 3 more open questions. The first one is, what would be use cases for Hardbit or HardGPT? Who needs them?
Yes, I answer live on this. So use case for Hardgpt, Hardbit. Hardbit is useless by itself, but it provides a possibility to lower costs for training ML models up to 10 times. So if you need, let's say, $1 million to spend on paying to doctors to annotating properly some data sets, now you'll have to spend only $100,000 to have a model with even better accuracy. That is how it works currently in NLP, and I cannot figure out why not everywhere. And actually, maybe it's time to share with you. These days, people are figuring out that transformers can be used not only in NLP, and there is a huge growth in usage of transformers in computer vision as well. So the things are going in that direction. Everywhere where recurrent neural networks were used up to 3 years ago, now recurrent neural networks are dead, and they are replaced by transformers. So everywhere where we used recurrent neural networks and convolutions in computer vision, for example, now we are using transformers more and more. And transformers means BERT and GPT-2, just different sub-use cases. And about so this is a use case for GPT-2. Why would about BERT? So why would somebody need BERT? To lower costs for training models for very specific downstream tasks, and to make more models, because if they are for sure there are much more institutions able to pay $100,000 for labeling data than those that can spend $1 million. So this is about BERT, and about GPT-2. It is about predicting incoming heartbeats in the same way as predicting next words, next sentences with preserved context in NLP, and these blah 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 words. So the technology and the logic is the same. You provide some, let's say, half of some array of data of bits, and you're telling to model, this is an input, and tell me what are you expecting in next 500 bits, and he will provide you statistically.
Okay, you can continue with the next question by Victor Domazetowski. So he has a pretty precise question. Thank you for your talk. I wanted to ask you whether you tried your model trained on MITDB on another data set. In a paper we have submitted for peer review currently, we got a result that these scores we are lowered by 90 plus accuracies to 70 when applied on different data sets, especially ones from different recording devices and with a smaller recording length. So the clinical use of these models is not as ideal as you mentioned.
Yes, it is far from ideal, and it's completely understandable and completely expectable, because models weights, learned parameters in the model within the models heavily depend on the statistics of the statistic parameters of the training data, and they are valuable only when they are applied over data with the same statistics parameters. And if apply them over some different data, it is obvious, it is expectable that you'll have lower accuracy, and that's the value of having foundation models, where you have where you trained your models with all, literally speaking, all reachable data, and then fine-tune that models to downstream tasks. Then those models have gathered the knowledge collected from all the data. You expose them while training them, and then it is much easier to train them for many downstream tasks like classification and so on and so forth. And we can expect that the accuracy will be much higher because we are applying them, I will say again, over data that they have seen previously. And that is not forbidden in the case of training models in unsupervised way. For supervised trainings, you have to split train and test data. For unsupervised way, no need for that.
Okay, before we proceed with answering the other 3 remaining questions, I also got another one on chat, which is, can you reveal something about the challenges you faced of deploying the solution, if so, if you had any?
Challenges about deploying the solution.
Yeah.
We have all the building blocks already in place. All we need is a team of software engineers that will collect them that will make a glue among the ECG recording devices, wearable devices, among AI models and alerting systems, and that's all. So only to make a union of all of these models already existing and provide proper, well architectured software solution, which is nothing more but like any other software solution. But you have to have a team of software engineers that will be able to do that.
Let me just add something. From 2016, we started with a project called ECG Alert. And for 2 years, we developed all the algorithms, which are based on signal processing, not AA. And we made a complete monitoring solution, which is software. And 2 years later, we were certified that this software is a medical device, which means that it satisfied all technical and quality management standards. So we deployed the solution on a cloud and we have it running. 2 years ago, we started with the data science team to improve everything we have and to make it much better and much more predictive. I would like to add something with the first slide of your presentation, Striki, about heart attack. Actually, I found in 2016 one research paper which said that heart attack can be predicted 2 hours before the onset of the attack. And this challenged me to do everything. So that's how we started the project. That's how we ended with this solution, what we have. Finally, the problem why we do not have complete solution for detecting heart attack is not because it cannot be detected, but we don't have training data. Because there are only few 2, 5, 10, 20, not more, ECG recordings of persons who got heart attack and they were measured in at that time. But we know that heart and human being is nature. It belongs to the nature. So it doesn't happen immediately. It's constantly moving towards that situation. So that's why we still believe, and I hope that very soon we will have some more data for training and we will have the solution.
Thank you for the elaboration on this question. I would like to proceed with the next one. Do you implement this model in real time in our health institutions?
Sorry, can you repeat once again?
Do you implement this model in real time in our health institutions? I believe
yes,
in our
we implemented this in the University Hospital of Cardiology here in Skopje, and they use it for so-called VIP patients.
Mm-hmm.
But we also sell our software to many other hospitals like NHS in UK, like San Donato in Milano, and some other hospitals in Mexico and Jordan. And we also started implementing our solution with Vodafone into what they announced, the first 5G hospital in the world, which is in Düsseldorf. And they are going to implement wearable sensors and our software as well.
Some amazing news there. Another question. I believe that, are you open to new members, interns? I believe you kind of mentioned this already, that you're open.
Strictly send an email, which is very easy to remember. And then please send emails and join us.
Yeah, okay. So another question. At the beginning of the session, the professor mentioned that the data should not be used outside of its origin country according to GDPR. Can you please elaborate more on this?
Well, GDPR says that data should stay in the country. This is mostly valid for European countries, not for other countries, but America also says data should stay in America. China, not to mention, it's forbidden to think about it. And this is why we have to deploy our solution on servers in each country. This is what we are doing at this moment in Italy and UK.
Okay, thank you. Another one. What? Stojancho, for you, do you see EKG data as low signal to noise data?
It depends. It depends on the data set, and even within the same data set, sometimes the data can be noised. Also, the statistics of the data varies over the time, and it depends whether a person is standing, sitting, or lying in bed. So it depends, and that's why we are doing a lot of normalizations to overcome these limitations and to make this the main trend of the line to make it flat. And this is first step for normalizing data. Then the ECG recording by nature depends on the bit rate, and bit rate depends on whether you're sleeping or you're running or doing whatever else. It depends. But the bit rates are also completely normal. Even they are fast or slow. It depends on what they're doing. So you have to somehow make all of this the data about each single bit comparable, and meaning that you are doing normalizing. And normalizing the heartbeat is not that trivial things, but I think that we are on the right track.
Thank you. And I believe we have one last question before we end this event. The last one is, how many seconds or milliseconds does your XG boost model needs to recognize that a atrial fibrillation that is happening?
It depends on the hardware, but if you're running this on some smart mobile, they're not on Internet of Things, but if you're running that on your mobile device, mobile phone device, then it will take up to half a second.
That's pretty quick. Well, I think that we can finalize this event. Once again, I would like to thank everyone who joined, especially our guests who took the time and effort to prepare this presentation and to show us what they've been working on in the past few months. Once again, big thank you to Stojancho, Professor Marian Gushev, Tomislav Ignatov, and Alexander Stankovsky. And of course, big thank you to everyone who took the time and joined us this Tuesday evening. Thank you. And
one last note, sorry for interrupting you. Once more, if anybody is interested to help in this, by joining our team as a data scientist, as a data engineer, or software developer, or cloud specialist, and so on and so forth, please join us and help to build some much more use cases with these technologies, because we have all the knowledge. We only need to put them in place. So
thank you. Thank you all, and I hope to see you very soon again.
Thank you for having us.
You're welcome.
Bye.
Bye. Bye-bye.